Okay. So, today we will discuss about maximum or minimum for real valued function. As I said that I have to consider real valued because maxima minima is always involves comparison. So, what is the setup? Again we have f. So, here I emphasize again, always we take, but here I emphasize U is open set in Rn, f is a function from U to R. Problem is to find a local maximum or local minimum. We have done this problem for function from intervals to R, we are going to do it for function of several variable. What is this local part, local maximum or minima? This means f is maximum locally, that is x naught in U is a local maximum or minimum if there exists a delta greater than 0 such that for all y in B x naught delta, of course, we are inside U. So, this ball should be inside U, I should not go outside. For all y in B x naught delta, maximum means f of x naught should be greater than equal to f y. So, around that x naught is maximum, value of f x naught is maximum, therefore, it is local. It outside this ball anything may happen, but around this ball there exists such a ball such that this thing happens, and for minimum or for minimum part f of x naught is less than equal to f y. This is a definition. You know, if I have a function of one variable, so recall if f is a function of one variable and x naught is a local maximum or minimum, that then you immediately have something that if f is differentiable at x naught. So, when you find maximum minima for one variable functional, you first try to find the zeros of this f prime, right. That is what the way you do it, that you given a function f, you try to find these zeros or so called stationary point or critical point, and at at maximum minima it will be f prime x naught will be 0. This is the first necessary condition. You know the proof also, I presume, but we will prove it for n variable. I will just stress proof is just one line, which works for n equal to 1 as well. But in n variable actually you do not even need f to be differentiable, there is a little bit of difference here. So, what happens that same thing will happen here. If f from this u in Rn to R and x naught is local maxima or minima, then grad f at x naught, this is 0, 0 vector, right. What is the difference? I have not written f is differentiable here. You remember grad f is what? So, directional derivative in the canonical directions. So, as we have seen in the very early week that existence of the directional derivative does not make f differentiable. That is grad this all these del f del xi may exist, f may not be differentiable, but in this case actually we have that f is even it is not differentiable, then it is grad f will be 0. What happens here, if grad f this exists is one variable, if this exists f is automatically differentiable, it does not happen in invariable. Okay. So, therefore, this comes automatically for n equal to 1. How do you prove it? If I prove this one, then I of course I have proved this one. Okay, let us prove it for, let us fix one direction, fix any direction E I. Look at the directional derivative. What I know? F of x naught plus t E I minus f of x naught equal to grad f x I at x naught into t plus mod t into E I h, where E I of h, E I of t h is t E I, E I of t E I goes to 0 as t goes to 0. Now, what happens? Suppose f x naught is local maxima. Okay. Now, what happens? This is, and so there exists delta such that all y in b x naught delta f y is less than equal to f x naught. So, if I take in particular t is less than delta, mod t less than delta, then f of x naught plus t E I, this is in this ball. So, this fellow is less than this. So, sign of this is always negative, always negative for mod t less than delta. Sign of left hand side is always negative. Come to the right hand side, this fellow goes to 0. So, t is very small, sign of this expression depends on sign of this expression, because whatever it be, this is I can make it very small. So, sign will be depending on this expression. Now, del f del x I x naught, this is positive or negative, I do not know, suppose positive, but t I can approach from negative and positive both sides, because I just need to ensure mod t is less than delta. So, I can take mod t a t negative. So, in that case this will be negative, as well as I can take t positive. So, this will be positive. So, right hand side will have both the signs according to t. If this is positive, I can take t positive to make it positive, I can take negative to make it negative. So, it will have both the sign, and this part will not matter, because this will be anyway very small as I take t to be very small. But this side always remain negative, it cannot happen, right. So, the only possibility is, so right hand side changes sign according to t. So, this, but this side is always negative. The only possible way is del f del x I at x naught is 0, but this is true for arbitrary I. So, grad f x naught is 0. So, this is a necessary condition for a local maxima or minima, that grad f x naught has to be 0, and this condition is not sufficient, and that is the one example, that is one very classical example for one variable you do it. Let me recall it again, that it cannot, it is not a sufficient condition that grad f may be 0, but it is neither a local maxima or minima. So, you know some classical example of for f from R to R, this famous function f x equal to x cube. Sorry, this looks like so f 0 is 0, should be look nice enough. F prime at 0 is also 0, 2x 3x square at 0 is 0. But if you take any neighborhood around 0, this side if you x is positive, this is positive, this is negative. So, there is no neighborhood where f prime 0 is bigger than or less than any point in neighborhood of 0, right, no neighborhood. So, in general I can conclude 0 is not local maxima or local minima. Similar example I can do for function of several variable. You can make examples in any n, I will let me make it for 2. F of x y equal to, let us say, y minus 2x square, y minus x square. So, what is the domain? Domain is the entire R2. Now, if you look at f of x y is y minus 2x square, y minus x square. Y minus x square is a parabola. This is y minus x square. Y minus 2x square is a parabola again, but this is little stiffer. This is y minus 2x square. And look at 0. F 0 0 is 0, and you calculate grad f at 0 0, this is also 0. But what about 0? Okay, let us take any neighborhood around 0, any delta, does not matter which delta. You see, if x and y comes from here, this is above this parabola y x square, so automatically above this parabola. So, y is bigger than 2x square, y is bigger than x square, so f is positive. Here it is below this y minus x square, so it is automatically below y minus 2x square. So, this is negative, so f is positive. But in this region, in between region, f is bigger than y minus this fellow, y is bigger than x square, but y is less than 2x square. So, here f of x y will be negative. So, in this shaded region f of x y is negative. So, around 0 0 you will have points where f of x y is bigger than 0, what is the value of f at 0 0, as well as points from here which is less than 0. So, that makes 0 0 is neither maxima, neither local maxima nor minimum, and such a point is called usually saddle points. Let me make a definition here. So, if grad of f x at is 0, then x naught is a possible candidate for local or maxima. So, x naught is called a stationary point or critical point, both the terminology is used. Critical point. If for every delta greater than 0, there exists y and z in b x naught delta. So, x naught is critical point, this is the assumption, and if for every delta greater than y and z, every delta greater than 0. So, if you look at any neighborhood around x naught, there exists y and z such that f of y is bigger than f x naught and f of z is less than f x naught. So, condition like this, that both the cases are possible, that it is neither maxima local neither local maxima nor local minima, x naught is called a saddle point. Saddle means once you climbing the mountain or some on the hills. So, there are places where it is plain. So, this side you go, this is you go down, this side you go up, and in between there is plain. So, it is called saddle. So, for that reason it is called saddle point. Okay. So, this terminology actually borrowed from function of one variable. Now, you know, for function of one variable, to actually check maxima minima, you go for so called second derivative test. So, let me recall what you do there. So, what you do there? First you check f of x naught equal to 0. Then you look at f double prime x naught. If it is greater than 0, you call it, then you say it is local minima, right. I am recalling what is what you have done already in one variable, you call it local maxima. Well, if you have seen the proof or not, it does not matter, but this is what you do, and you see there is a connection. If you look at f of x naught plus h minus f of x naught, h in a neighborhood of x, so h less than delta, then if f x naught is a local minima, then this sign will be always positive, f x naught is bigger less than anything around it. So, sign of f x naught plus h minus f x naught is actually the sign of f double prime x naught. And similarly, if it is local maxima, this will be always negative, that is the sign of f double prime x naught. So, and this is local maxima or minima depends on, in a neighborhood this is always positive or negative, and that sign depends on the sign of f prime x naught, f double prime at x naught. Why such a thing is happening? Let us try to see one justification for such a thing in case of function with several variable with taking value in R, and that will of course say what happens there in the special case of n equal to 1. Well, we look at in Taylor's formula. For m equal to 2. So, how to write? Instead of y, I write f of x naught plus h minus f of x naught. What is that? If you recall, summation I. So, that is actually grad f at x naught h plus half f double prime z h. Right, where z is a point in the line joining x and x naught plus h, or other way around, correct, where okay. Now, x naught, if local minima or maxima, local maxima or minima, then we have already known grad f x naught is 0. So, f x naught plus h minus f of x naught, this is actually half of f double prime z h. Now, write it, I write it in this formula, summation I equal to 1 to n, j equal to 1 to n, del square f del xi del xj at z hj hi. Okay. So, sign of this fellow will depends on sign of this quantity here. Now, suppose del square f del xi del xj are continuous for all ij. Then what I do? I write it as half of let me write it in this form. I just subtract what I have added. Okay. So, this fellow is here, half of f double prime at x h, oh, h j h I was missing, x h plus half of h square e h. Now, look at this. This is less than half of xi xj x naught. I made a mistake here. This is x naught This was the correct expression. Please correct your notes, or if you are looking back, just look back at the expression there. This would have been correct. I just missed it. I hope you followed. Now, see what is happening. If I assume these are all continuous, Z is in between this interval. So, I can choose H very small. So, I can choose delta such that if this is small, then sine of f of x naught plus h minus f of x naught is determined by sine of okay. So, that is it. The informal explanation of why this maxima minima, the sign is determined by the second derivative. Instead of second derivative, here I have f double prime x naught h. So, next lecture we will make this argument, because this is just informally I have written down. We will make this argument formal, write it in a better notation, and try to derive the test for the actual second derivative test for checking maxima minima. So, that is next lecture. Thank you.